Hello, hello, hello. Hi, everybody. Thank you for coming today. I'm Jeff. I'm the co-founder and CEO of Chroma. Chroma is an open source vector database. I thought to calibrate a little bit, I always like to do a bit of a show of hands. So I know everybody's in like the post-lunch sleepy period here. I know that I am for sure. But maybe just, by show of hands, like how many people have heard of a vector database? Raise your hand. Okay, amazing, that's 100%. How many people have used Chroma? It's okay if you haven't. Okay, that's pretty good still. Awesome. Well, I'm really excited about that because I don't really want to talk about, the nitty-gritty of setting up a RAG application for the first time. I think most of you already have that context, and that would just be repetitive and boring, and I want to keep you awake and not put you to sleep. So my goal for today is to give you a bit broader of a view about what is happening in the software world right now, and how should we think about it. So here's some background. It sounds like the room does not necessarily need this background, but Chroma is an open source AI native vector database. We've had kind of over 2.2 million downloads since launching in February. We're doing about 25,000 downloads a day right now, and we have a great community, and it's been really fun. People love Chroma for its simple and easy to use API. So here's my assertion. My assertion is that AI is smart, but it doesn't know anything. And I'm sure this is not lost on you all. You all have been thinking about AI, playing with these tools, seeing what they're capable of. And it seems very obvious that language models are very good reasoning machines, and they're just getting better and better. But we still want the ability to be able to program their memory. And why do we want the ability to program their memory? We want the ability to program their memory because we want them to do useful things that we tell them to do and want them to follow our instructions. As it turns out, this is not trivial. Not necessarily trivial for humans communicating with other humans, right, as a comp, but also not trivial to communicate with an agent or with an AI. Why do we want useful directed intelligence? Well, ultimately, I think that we all share the view that if we had more intelligence in the world, we could solve more of the world's problems. We could have more democratized access to medicine, more democratized access to education, more democratized access to software, more customized software, and just in general, we would make a more flourishing for all of humanity. So that's why this problem matters in the biggest sense. So I use this analogy a lot. What I want as a developer is I want the ability to be Tank in the movie The Matrix. So I know it was a long time ago now, but if you recall, Neo is yanked. He takes the red pill. He's yanked out of the Matrix. He gets put onto the Nebuchadnezzar is the name of the ship, and Tank plugs him in for the first time, and he plugs him in, and then he starts downloading all of these like fighting routines basically into Neo's brain, and then Neo wakes up and has the famous line, "I know Kung Fu," and then goes into the dojo and fights Morpheus, and it's awesome. This is the ability that I want. Neo is the language model, Tank is me, and I want the ability to download specific instructions and information, how to use tools, what facts to reference. That's the world that I want to live in. And the bigger picture here, I think, is this macro secular shift. If we think about AI, it's easy to trivialize it down to something like, we're building a retrieval augmented generation use case over our HR knowledge wiki base. Which is great, and I've done that, and I think everybody should start there. But I think in a much bigger picture, what is happening in the world is we're moving from software 1.0 to software 2.0. And if you're fans of Andrej Karpathy, you will see that this is directly cribbed from a blog post of his from 2017 where he makes the same case. And I encourage you all to go look up that blog post and read it because it's incredibly prescient and incredibly has an amazing amount of foresight into what's happening right now. But if you think about it, traditional software development is actually limited by code. And it's limited by the complexity that humans can write code in. Code can only do so much. There's a great XKCD comic I'll have here on the slide in a minute to sort of prove the point here. But if you think about the blue circle, the space of all possible programs, particularly programs that interface with the real world, where the real world is messy. Types are all the rage these days. Everyone loves TypeScript. I do too. But types require very strongly typed inputs and very strongly typed outputs. They do not interface very well with the real world because the real world is not strongly typed. The real world is messy. But what's beautiful about AI is that it's increasing the scope and the possibility of the kinds of programs we can create because AI accepts messy inputs and gives you messy outputs. And this is a feature, not a bug. So to prove the point a little further here, if you think about software 1.0, this is development only using code, versus software 2.0, which is development using AI. We're moving from a deterministic to a statistical world. We're moving from an explicit to an implicit world. We're moving from a world where all of the execution is determined by the code that you write to moving to a world where execution is defined by the data that you give the model access to. And I have a whole slide on this in a little bit, and we're going to go into more detail about what that means. But of course, we want the same things. We want to be able to create systems that are testable, that we can actually evaluate. We want to create systems that are debuggable and fixable, and systems that are fundamentally observable and monitorable. And as I'm sure all of you have experienced, there's this problem in AI, and it's been a problem for a very long time. And the problem is that demos are easy, but production is very hard. Reliability is very challenging. With a small piece of code, you can write a unit test, you can scope in exactly on the right inputs and outputs, and you can be very confident, 99.9% of reliability confident that that piece of code is going to do what you think it's going to do every single time. Maybe besides like background radiation from the universe, flipping bits, which is pretty rare. With AI, it's not the case. You can build a piece of software using AI. It can work well in the lab, but you put it out in front of your users, and all of a sudden it starts falling over. And it's not a great experience. And I think this has been true about AI since AI was invented. This is true about traditional deep learning, and it's also true about language models, and it's also true about embeddings. And so the question becomes, how do we solve this problem? So here's a great tweet that's also in that blog post. Anshul Kapathi tweets, "Gradient descent can write better code than you. I'm sorry." And this this user replies with this the classic "what" meme. Okay, so I promised some XKCD, and here it is. So XKCD is still right about this. So I'll read it. If you can't read it in the back, I will read it. So the guy here down in the bottom left says, "This is your machine learning system." And the guy on top of the pile says, "Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side." And the guy in the bottom left says, "What if the answers are wrong?" And the guy on top of the pile says, "Just stir the pile until they start looking right." And by the way, this is I think in 2018 or 2019 this came out. Again, if you've built anything with retrieval, embeddings, language models, this is still the case. It is the same thing. It is still AI. But XKCD is not right about everything. Some things have changed. And so again, to read the comic on the right, the man standing here asks, when a user takes a photo, the app should check whether they're in a national park. And the woman sitting at the computer says, "Sure, easy GIS lookup, just give me a few hours." And then the man standing says, "And check whether the photo is of a bird." And the woman says, "I'll need a research team and 5 years." And then down at the bottom it says here, in computer science, it can be hard to explain the difference between the easy and the virtually impossible. It is no longer virtually impossible to do this. I think all of you strongly believe that you can hand any photo to the GPT-4 Vision API, and GPT-4 Vision can answer this question every single time with a lot of robustness and a lot of reliability. So to get kind of abstract for a second, what do we want? We want to be able to create programmable memory for AI. And what does programmable mean? And this is what programmable means to me. I want to be able to change a system, that's an input, and I want to be able to have an expectation of the change in the system or the output of that system, and I want that expectation to match reality. Again, kind of an abstract framework, but I think if you think about a small little function, when you're changing the code, what are you doing? You are creating an expectation about how when you change the code, it'll change the reality of how that function works. That works pretty well in code most of the time, not all the time, but it works basically not at all today using data. And this is a big problem. To prove the point, if I told you, take your current corpus of documents that are loaded into Chroma and then add in this new corpus of 100 documents, what's going to change? Very hard to tell. Very, very, very hard to tell. Today, things are not programmable, and this is a problem. So what we want to be able to do is we want to be able to program AI with data. We want to be able to change the data and then change the behavior of the system. Again, software with AI is changed by changing the data, not by changing the code. And so if you look at the classic kind of funnel here at the bottom, these series of arrows, we have an input that could be from the user. We augment it with a context. That could be retrieval. So you go to the vector database and you pull out the similar documents and you load them into the context window. Those go through the weights of the language model, and then out the other end flows the generation, the output of the model. It streams its tokens. And of course, how does data change this system? What are the influences? What are the levers? What are the knobs that are being tuned here? The data at inference time changes the context. The data at training time changes the weights, or fine-tuning time changes the weights. And so then the question becomes, how do we know how to change the data at context time, at inference time, or the data at training time? So this is a bit of an aside, but I think it's actually a useful framework, and I've not seen it shared anywhere else. And hopefully, as you're getting the sense of during this talk, I really like to think in models, and I feel like the world has a lack of models. Models are useful. They're always wrong, but they can be useful. So here's one model that I've been thinking about, and would love to know your all's perspective on as well, maybe after the talk. And so this is your classic 2x2. No, I'm not a recovering management consultant, but I still can make a 2x2. And so you have fine-tuning and no fine-tuning, retrieval and no retrieval. And the question is, how many use cases and what type of use cases fall into these various buckets? And I'll make the disclaimer that I think that my assertions here, which I'll walk through in a second, are true about the world today, but maybe not true about the world 3 months from now. Things are very dynamic. Things are changing a lot. But I think this is true today, that where you want fine-tuning and retrieval, which is the top left box, are the situations where the use cases are the very most demanding. So this would be use cases like law or medicine. The way that I like to think about fine-tuning is you're teaching the language model almost how to think. You're teaching it a new language. You think about, you hear your doctor, transcribing to a person different notes about your visit. It almost is a different language. You can't understand it at all. And of course, the weights of GPT 3.5, GPT-4, models from Cohere, Google Palm, et cetera, they've been trained on the internet of data. They've been trained to speak normal English, not doctorese and not legalese. And so I think fine-tuning is especially useful and important where you want to teach a dialect to the language model. And so fine-tuning plus retrieval, you both want to teach a dialect and you want factual information, up-to-date, interpretable, reproducible, factual knowledge, fine-tuning and retrieval. Use cases where you want fine-tuning and no retrieval, I don't know. I don't know what use cases fall into this bucket. I think maybe some use cases where you want like style transfer. So you want the language model to talk like it's Aristotle, but you want it to do that from its weights and not from the prompt. But you don't want any of Aristotle's actual knowledge. You want it just to think like Aristotle. Maybe that's a use case for it. Again, I don't actually have conviction here. That's why it's a question mark. If you have conviction, please come tell me afterwards. Bottom left, so no fine-tuning and retrieval. I think today, this is 90% of production use cases. So going back to that slide where we're thinking about what are the useful ways to change the data today? Change the data with a disclaimer of today. Change the data at inference time, which is about retrieval. Change the data at training time, which is about fine-tuning. I think 90% of production use cases need retrieval, but not fine-tuning. Just my opinion. And then lastly, the last bucket is no fine-tuning and no retrieval. And the intuition here is just about anything you can do just fine in ChatGPT today is exactly that. ChatGPT is not fine-tuned at all on your data, and ChatGPT does not have access to, typically speaking, maybe ChatGPT plugins is a bit of an exception here, but those are not widely used. ChatGPT does not have access to your data. So this is a 2x2 that I think is useful to think about kind of the state of the world today, and when we think about wanting to change data to program AI, what data should we be changing in most use cases? And I'm making the case that retrieval is where in most use cases we should change the data. Okay, so this is a bit review, I think, for this audience from the poll of hands earlier. But what is the task for retrieval? To some degree, you could say that the task of retrieval is for the working memory of an AI model, which is its context window, what knowledge out of all possible knowledge in the world should be inside the context window? It's kind of a search problem, but it's also an optimization problem. Search just gives you a rank-ordered list of all 110,944 results that match your query. Optimization has to think about extra concerns. It needs to think about actually, how is the language model going to interpret this information? What information might distract or confuse the language model, not just what information is most relevant? And so this analogy I use quite a lot, and I really like it. If you think that it's wrong, you can come tell me, and I might update my priors. But the way that I like to think about it is the following. You have an AI. It is sitting at a desk. There is nothing on the desk. It is an empty desk. And the AI is handed a task. The task is a piece of paper. The context window of the model, right? The piece of paper. And then the question becomes, if this task, what information? Given this task, it could be a user's question. It could be a user's task. Hey, go book me a flight. It could be a question. Hey, what is the company's time off policy? What information should be on the desk? And this is both relevant to factual information, like the company's time off policy, but it's also relevant to tool using information. So if the user says, book me a flight, you might want to identify which API is the best API for flight booking. And as it turns out, embedding similarity search is still quite a useful tool for selecting the best tool. There's actually a pretty famous paper now. I think he's speaking here at this conference, actually. Dr. Jim Fan from NVIDIA wrote a paper called Voyager. In that paper, he created a Minecraft agent that was both sort of knowledge acquiring as well as tool using, and it used Chroma. So again, I really like this analogy. I think it simplifies the problem. It makes it quite intuitive. So this is another more detailed way of thinking about it. What kinds of information exist? So there's the interior world, and then there's the exterior world. So the interior world would be giving the language model tools to reason about time and knowledge. So there's past, which is obviously knowledge. There's the current, which is awareness of its existing context. And then the future, which is planning. And you'll see agentic systems oftentimes use all three of these different strategies to create dynamic knowledge for agents. And so agents don't need to just know about Wikipedia, but maybe also need to know about, what am I currently planning? What do I want to do next? What should I do next? And a retrieval system can help a lot there. On the other side, AI agents need to have knowledge about the exterior world, not just the interior world. Be able to reason about tools and people. So tools would be code or APIs, other agents, of which we don't necessarily have. I have a question mark here because I don't think we really understand yet what this interface means. Will agents talk to agents in embeddings? Will agents talk to agents in natural language? Will agents talk to language via APIs? We don't really know yet. And maybe it would be all these ways, but there certainly would be some predominant ways. And then lastly are humans. And of course, agents and humans interact via UI. And so what you want is a ability to see and program all this knowledge in a way that is, yes, accessible and useful by the AI agent itself, but also by the humans that run the system. So interpretability is obviously a really big problem in language models, and classically, all of deep learning. So these neural nets are incredibly powerful. They can learn these incredible abstractions, incredible patterns, but understanding which node in the neural net does what, and how they chain together, and how this math works, and what it even means, and how to make the systems interpretable. I mean, this is sort of the problem of AI safety. It's a really big problem, and we don't know. So having accessory systems like retrieval, where you, the human, can go inside and see exactly what's going on, and you can change that information instantaneously, pretty big deal. It's a pretty important thing. So this is also probably review for the audience, so I will spend not a lot of time here. But of course, the magic of embedding space is that you take a piece of data that the bits on the disk have no meaning, right? It's all just ones and zeros, so the computer doesn't really understand what it means. It's just ones and zeros. And you're able to turn it into a new and different representation that the computer can understand. It is a map of meaning across your data. People typically talk about using embeddings these days for retrieval, for language models, and that is a really great use case. But vectors and language models can also be used in the reverse direction, where you use language models to better understand your data. And there's a bunch of really exciting work going on here, and maybe if that's interesting to folks, we can take some questions about that at the end. So here's one really simple example of how this works. I don't know if this is legible at the back of the room, but I'll walk through the highlights of how semantic similarity can be useful for even tasks where you intuitively would not think that they would work. And so in this example, this is Python. We import Chroma, we create a Chroma client, we create a collection to put some documents in. We load in the documents apples, oranges, and pineapple. So those are the documents, just these single words, apples, oranges, and pineapple. And then we query that collection, and we say, give me back the single nearest neighbor result where the query text is Hawaii. And so, again, as a human, I think that any of us would pass this test. Which fruit is most similar to Hawaii between apples, oranges, and pineapple? It's pineapple. And in this case, it gets it right. It gets pineapple right. So this is just an intuitive, a very simple example that I like because I think it proves the point of the ability of free association that these large embedding models have been trained on and the abilities that they give. Okay, we are landing the plane here, but how do we actually know what data to change? That is the fundamental question. And I don't know that we all have the answers yet. I will be honest. I have some ideas, which I'll share on the next slide or two. But this is a big challenge, I think, for the entire industry. This is the challenge of going from software 1.0 to software 2.0. We know how to write code. We know how to change code. We know how to write data, but we don't really know yet how to change data. And we need to figure this out. So here are some ideas. And this is the most information-dense slide of my talk. And so I make the case here that actually also vectors, also embedding space. This is another extremely useful tool in our toolbox to decide what data to change. And so here are 3 simple ideas of ways to get started. Whenever I give a talk, I try not to just repeat the same thing that's been repeated 85 times online. I try to always create some new content. And so this is fresh. This is new. I've not seen anybody else talk about this. So world's first. So let's walk through these 3 or 4, I guess it's 4 different strategies. So number 1 is to simulate a bunch of queries through your system and then label them with a language model, by hand, or both. Again, talking about AI and its power is that the inputs can be dynamic. The inputs can change. Of course, this is also a con because the inputs can change. And so to get confidence about the system you've made and its capabilities, it's a good idea to just generate a bunch of test cases of it going through different paces. In the same way that if you built maybe a part for a car, you would drive through the snow, you drive through the desert, you'd maybe hit it with a hammer. I don't know. I'm not a car designer, but you would do things like this to stress test this part. What is it capable of? Where does it fall over? You want to get confident to be able to reason about that. And I make the case that hand testing alone isn't necessarily good enough for this. Because, I'm like you all. I'm probably going to write 10 or 15 tests by hand and then call it a day because it's kind of boring. But the cool thing about language models is that the language model can write the question for you. So one strategy that people have been adopting to do this is they take all of the documents inside of the vector database, and then they just ask GPT-4, please write me 3 questions that somebody might ask where this document is the answer. So it's the opposite direction. You're not going from question to answer. You're going from answer to questions. And then that gives you now a document set. And obviously, you can go through and hand curate, okay, did GPT-4 do the right thing or not? But once you have that data set, now you have a benchmarking data set to do eval on. And obviously, you can expand sort of the types of things that it does and try to find where it falls over, find its edge cases. And all of these queries, by the way, are also embeddable. And so I think a very interesting strategy here, when you think about number 2 here, what to add, is compare the distribution of queries and documents to find holes in your embedding space. Or if you're a programmer, this is sort of like the fragging approach. You're trying to understand, where do I need to add more data? And intuitively, if you look at this diagram here, I'm not sure what data set this is from. It's an illustration I found on the internet. There are holes in the embedding space. So there are some things like this orange area where all of your data from test, which might be real world data, overlaps very nicely with your data in training. Or your data in training in this case would be the data that you've put into your vector database. So this is your queries, and the other one is your answers. And so orange, I think, is going to do a good job because orange is fully self-contained inside the orange cluster over here in train or in the document corpus you've loaded in. But other things are not like that. So for example, there's a lot of data here from the green and blue classes, where if I look over here, there's no relevant documents. And so again, thinking about visualizing embeddings is this very useful way to semantically understand what things does my language model know about and not know about, and what things do I need to teach it to have it do a good job. Another strategy that's not listed here that I think actually will become very popular, but I've not seen it very prevalent at all yet, is the idea of fencing. And fencing would be the ability of, with a new user's query, you make sure that it falls in a cluster where you think it's going to do a good job. And if it doesn't, then you reject it somehow. You either cancel it or you route it over to a human. Again, we want to get these production AI systems from a place today where 80% or 90% reliability is doable but very hard. We want to get to a place where we can deploy something with 99.9%, even 99% confidence, know it's going to do a good job time and time again. And so I think fencing will be a pretty popular strategy to do that. So number 1 is test, simulate a bunch of data. Number 2 is figure out what new data to add. Number 3 is look for data to change. So look for failure cases where the retrieval gathered the right documents and then rewrite those documents using a language model to make the information more clear. So just like a human being, even though you've provided the information to the language model, it might not be able to synthesize it correctly. It might get confused, it might get distracted. And so sort of reifying and changing the documents inside to make it easier for a language model to understand, I think is a really powerful idea. And then number 4, look for ideas of what to remove. And if you think about it, it might be okay if you have a whole cluster over here that never gets any queries. It probably won't break anything. It's making it more expensive, but it's not the end of the world. But there are cases where there are very similar documents or embeddings that you should consider merging them together. And I think you should consider merging them together or defragging them, because if you think about it, if you have a query and you get the 5 nearest neighbors, and then you put those 5 nearest neighbors into the context window, it doesn't help necessarily to tell the language model the same 5 things over and over again in different ways. There's kind of a trade-off between homogeneity and heterogeneity. You want to make trade-offs between what data is most similar to this versus what data is in the vicinity of this query. And so defragging or merging data points that are very close together in embedding space is another very powerful tool to figure out what to remove. So these are embryonic ideas. As I said, I think we're all very early in understanding how do we change data to program AI. But I think if you think about what do you do when you code something, you write tests, you add code, you change code, and you remove code. This at least is one step forward for doing the same kind of thing with data. It's a way to write tests, it's a way to add data, change data, and remove data. And I think that this is a step in the right direction. And if you want to work on Chroma's applied research team or engineering team writ large, come find me. But particularly our applied research team, along with applied research teams inside of academia, I think will be moving more and more and more forward to finding ways to creating production AI. And one final note here, because I have an extra minute, that I think is very interesting to know about, and I thought that I would tell you all about it as well, is what does the future of retrieval look like? So today, as you all are probably pretty familiar, it's sort of dumb. So you retrieve some English, you throw it in the context window, and then it streams out all the generation, all the tokens, and then you're done. But what's happening inside academia, and I'm happy to point people to the link here if you're interested, is a few very interesting things. So number 1, people are moving from one-shot retrieval, where you retrieve one time per generation, to continuous retrieval, where you're re-retrieving over and over again as you're streaming out tokens. You might stream out some tokens, embed it, retrieve, back up, restream, and it's like this thing where you're sort of, again, hand querying, you're steering it. You're steering it to give you the right answer. It's very, very, very interesting. And number 2, you're also seeing people move beyond the sort of dumb version where we only throw English or natural language into the input layer, and moving towards a world where we can actually use embeddings themselves as ways to, put our finger on the scale to steer the language model at the intermediate layers as well, inside of the language model. So not just English for embedding-based retrieval and steering, but also embeddings themselves as well. So this single to continuous, and then English only to English plus embeddings. Both of these are very interesting trends in retrieval happening today in academia. If you go to an academic conference about retrieval, similar room, this is what they'll be talking about. And this is, I think, coming down the pipe. And of course, our goal, going back to the very beginning of the deck, is to create production memory for AI. And we want to create production memory for AI because we want to create systems that are useful and dependable. And we think that if we can create systems that are useful and dependable, we can all change the world. So thank you very much.